we introduce RISE-SDF, a relightable information shared signed distance field for glossy object inverse rendering. Inverse rendering aims to reconstruct the 3D geometry, material parameters, and lighting conditions in a 3D scene from multiview input images. To address this problem, some recent methods utilize a neural field or 3D Gaussian combined with a physically based rendering model to reconstruct the scene parameters. Although these methods achieve impressive geometry reconstruction for glossy objects, the performance of material estimation and relighting remains limited. Given multiview image and their corresponding camera pose, our end-to-end relightable neural inverse rendering system achieves high-quality reconstruction of geometry and material properties, thus enabling high-quality relighting. In our pipeline, we use a combination of progressive hash grid and neural signed distance field as the geometry representation. Further combining volume rendering with traditional physically based split-sum approximation using differentiable mipmap. We apply information sharing MLP architecture to achieve stable convergence of geometry and material. Furthermore, in order to handle indirect illumination, we incorporate indirect MLP during training and a novel second split-sum rendering algorithm during relighting. Our first stage starts with geometry reconstruction. Given the camera pose, for each pixel, we sample a view direction D and then use ray marching to draw the volume samples and render the pixel color. Given the location and view direction D, we first compute their positional encoding and spherical harmonic encoding for the reflected direction. Then, we use the progressive hash grid with the geometry MLP to predict the geometry feature and follow news to get the corresponding normal vector Ni and volume rendering weight Wi. After that, we decompose the per sample radiance to a weighted average of diffuse and specular radiance. These two values together with the blending weight are predicted using three different MLPs, with the geometry feature and the positional and directional encodings as the input. In the second stage, we treat each volume sample as a small surface, and divide the per sample radiance into specular and diffuse radiance using split-sum approximation. If we compare the equation of stage 1 and 2, we can observe that both blending weight and metallic Mi are used to mix the diffuse and specular part. Besides, diffuse color and albedo are both view-independent and low entropy. Therefore, based on the MLP structure in stage 1, we share this information among the diffuse and blending network, and add another roughness network as well as the differentiable mipmap. This information share framework makes sure more stable training of the geometry and material. We can observe that with full pipeline, the geometry and material reconstruction quality are higher. So far we have excluded indirect illumination from our model. To improve the inverse rendering quality, we add another MLP to predict indirect illumination. Note that we only estimate the indirect illumination once at the surface intersection for one primary ray for efficiency. Our full model uses the MLPs to predict per sample values, and aggregate them using volume rendering. Then use the indirect MLP to refine the specular part of the radiance. During the relighting stage, we cannot reuse the learned indirect illumination MLP for unseen light conditions. Therefore, we propose a novel second split-sum for relighting. Different from Monte Carlo sampling, we trace a single ray and use the split-sum to approximate integration over the reflection lobe. We compare our full pipeline with the pipeline without second split-sum, or indirect illumination prediction. Models omitting the second split-sum and indirect illumination show significant degradation. The former latter exhibits unnatural contrasts due to the indirect ML trained in the different light condition, while the later displays reduced realism in reflections. We show our result on geometry reconstruction and the corresponding training time for different methods. We can find that our method has the best geometry reconstruction quality in this scene. In this case, we can observe that although Nero is SOTA, it tends to reconstruct too smooth surface and lose a lot of high-frequency signal on the spoon, while other method fails to reconstruct high-quality surface. We also compare the albedo and roughness estimation. Both shows that our algorithm has the best performance. We compare the relighting between our method and other methods. We can observe that NVIDIA has some color shift due to the MLP light representation, NMF has high noise due to the Monte Carlo sampling, while Gaussian shader has artifacts due to the geometry representation. If we compare our model and Nero in detail, we can find that Nero has aliasing effect due to the exportation to the triangular mesh. Here is the relighting result in another scene. We can observe that other methods either have aliasing effect or blur the light information. We also show the relighting result under multiple unknown light conditions. Here are some geometry reconstruction result on the real dataset. We also show some material reconstruction and relighting results. Although we achieve superior performance on the reconstruction, inverse rendering, and relighting of shiny objects, our system still has some limitations. For example, as shown in this case, shadows are not well represented. This will cause ambiguity between shadow and geometry. Thanks for your watching.